Hi, today we are going to talk about the pre-stressed concrete structures. So far we have talked about the reinforced concrete structures. We went through the analysis and design of reinforced concrete structures, but now we'll be talking about the very noble concept of pre-stressing and how it affects and enhances the performance of the concrete structures. These are some very simple and basic examples of pre-stressing that you can see around yourself. In the first example, as you can see here, if you apply the horizontal forces, you can hold the stack of books like this one, and if you apply enough force, probably you can put a load and the books will be able to take that load as well. So this is a very simple example of how the books can take the load when there is enough pre-stressing applied there. And another very good example is these liquid barrels. In these liquid barrels, these steel rings are pushed from the top and the bottom, so they are in tension and they apply compressive stresses to these wooden planks. And due to these compressive stresses, these wooden planks are held together. So it is so efficient that it can even hold liquid as well. And another very simple example is these bicycle spikes. As you know, these small screws here helps to tighten these spikes, and it puts these spikes in tension, and this will help to take more compressive load from in the wheels as well. So these are some very basic examples of pre-stressing, and this very concept can be applied in concrete structures to enhance the properties of the concrete structures. Now, in concrete structure, as we know, as the tensile stresses in concrete exceeds the tensile strength of the concrete, cracks will appear. Now, if we apply the compressive stresses in the concrete even before the load is acted on it, which is done by tensioning these pre-stressing tendons. So these pre-stressing tendons are put to tension first and then are anchored here. These are anchors, and then they are cut. And so the tensioning of this pre-stressing wire will apply uniform compressive stresses in the concrete. And these compressive stresses will help to counteract the tensile stresses that are developed from these external loads. So if we can counteract those tensile stresses, then we can prevent the cracks from happening in the concrete as well. So this is the main essence of pre-stressed concrete. We apply the compressive stress before the load is acting in the concrete so that it counteracts the tensile stresses generated by the external load. Now, as I discussed earlier, the main disadvantage of reinforced concrete is that it will crack. The crack in the tensile joints are inevitable. So when the concrete cracks, it reduces the effective area of the concrete, and which will contribute to its moment of inertia. So the reduction in the moment of inertia means the deflection will be increased because the stiffness has reduced. And also the excessive cracking can be a durability problem as well. And also in the reinforced concrete structure, we are not taking full advantage of the high strength steel so far. So these are the main drawbacks or limitations in the reinforced concrete structures, which can be overcome in the pre-stressed concrete structures. Now, in the pre-stressed concrete structure, as I already said, this uniform compressive stress is applied in both the side of the concrete beams, and then these compressive stresses will counteract with the tensile stresses. As you can see here, the external load is causing the tensile stresses at the bottom, and this is the compressive stress. So this compressive stress that is caused by the pre-stressing will counteract with the tensile stresses due to the external load, and the final stress diagram would look something like this one. That means that there will be a very small tensile, there may be very small tensile stress remaining, but that is not enough to make the concrete crack. So that is a big advantage for prestressed concrete structures. And another thing here you might have noticed is that due to the application of these compressive stresses in the concrete, you can see that the beam is bending upward. So there is this upward deflection, which is called as camber. Now that is a good thing as well. So if we have an upward deflection due to the prestressing, then when the external load acts like this one, the deflection due to the external load is reduced because we already have a cambering in the beam. So the external load deflection, total overall deflection is reduced. And also in the cantilever, the second example, as you can see, due to this initial compressive force, the beam is bending upward, and when the external load is acting, the deflection is actually maybe even 0 or very small. Now there is another advantage of prestressing in concrete. It also improves the shear capacity compared to the ordinary reinforced concrete structures. And apart from that one, in prestressed concrete columns, the flexure capacity is higher than compared to the structure without prestressing. For example, this is the moment interaction curve, as you know, or we call it MN interaction curve. Now we discussed about this one earlier, that this region where Ku is less than Kub is the tension control region, and that is the ductile region. Now most of the columns are designed within that region, and as you can see in this region, as you go on increasing the axial load, your moment capacity is also increasing. So in the columns in the typical design region, as we go on increasing the prestressing force, your moment capacity will also increase. So that is another advantage of prestressing. So to summarize, the advantage of prestressed concrete structures are: it will delay the cracks appearing in the flexural members, because we are applying the compressive stress that will nullify the tensile stress, so it will delay the cracks appearing in the concrete structures. And that means that the tensile stresses under working loads, it can be nullified. The cross section is more efficiently used in the concrete. If there are no cracks, it means that the flexural members are much more stiffer, because the moment of inertia is contributed by the whole concrete section. So it is much more stiffer than the reinforced concrete structures. And also, as we said, the cambering caused by the prestressed concrete prestressing force will actually help to reduce the overall deflection as well. And also, prestressed concrete members have improved resistance to shear again compared to the reinforced concrete structure. And also, for the prestressed concrete structure, we mostly use the high strength concrete, mainly because the concrete has to withstand of a high compressive force. So we usually use high strength concrete, and also the prestressing tendons used in the prestressed concrete structures are of high strength as well. So when we are using the high strength concrete and high strength steel, we can use a very slender members in prestressed concrete structure, which you can see in this example as well. This is a prestressed concrete beam, and you can notice that how the sections are very slender in this structure. But there are some limitations in prestressed concrete structures as well, and one of them is the cost as well, the high cost. For normal structures, prestressing can be very costly, but for long span bridges and high-rise buildings, it can be a alternative good solution, and it can actually be cost effective as well. But for normal structures, it can be expensive. And also, the prestressing that we apply, the tensioning that we apply in the tendons or the steel can be lost during with time. So the loss of prestressing can be caused due to the shrinkage and creep in concrete, or it can also be caused due to the relaxation of steel stresses. So this loss in the prestressing wires will affect the strength of the prestressed concrete structures. So that is one drawback, limitations as well. And the loss of the pre-stress in the steel can also be due to the anchorage slip as well. What it means is that we have this pre-stressing wire and it is locked in this anchor, probably with the ways like this one, and when we apply the pre-stressing and we remove the jack, there will be some anchorage slip here, and due to this anchorage slip at the anchors, there will be some losses in pre-stressing as well. So that can also reduce your capacity in the structure. And also the design and construction in the pre-stressed concrete structure is usually much difficult than the reinforced concrete structure. So there are these limitations, but for particular structure, for specialized structures, pre-stressing can be a good solution. And now let's look into the different materials that we use and their properties in the pre-stressed concrete structures. For pre-stressed concrete structures, we use high strength steel, which has strength much more than that we use for the normal reinforced concrete structures. The earlier attempts of using pre-stressed concrete structures, the engineers tried to use normal strength steel in the pre-stressed concrete as well. But the problem was that with the normal strength steel, we can stress it to certain amount only, and there is of course some pre-stress loss as well. So when the pre-stress loss is taken into account, then the pre-stressing that is there in the steel is quite low. So that means with time the pre-stressing is lost and the structure strength is also reduced considerably. So pre-stressed concrete structure was not so successful when it was first discovered. But nowadays we use high strength tensile steel, which has strength capacity much more than the normal reinforced concrete structures. So these tensile steel will have your yield strength or the tensile strength much more than that of the steel that we use for the reinforced concrete structures, and they are usually very thin wires, usually of 5 to 7 millimeter diameter, and they are bundled together like this, and that these wires have a very high tensile strength, and they help to, and having these small wires will help to improve the bond between the concrete and steel as well. And as you can see here, the strength and strain curve for the pre-stressed tendons and bars, as you can see, the tensile strength of these pre-stressing wires are much higher than the 500 megapascal that steel that we use for reinforced concrete structures. So these are much higher than the 500 megapascal that we use for reinforced concrete structures. And this table also shows the diameter and the tensile strength of different wires and bars that we use for pre-stressing. As you can see here, the wire that are 5 and 7 millimeter diameter, the minimum tensile strength is 1500 to 1700 megapascal, which is again much higher than 500 megapascal that we use for normal steel. And also for the we can also use bars, high strength bars for as pre-stressing member, and these again have a very high tensile strength compared to 500 megapascal steel. And this is a picture of an anchor, how the pre-stressing wires are held at the end for post-tensioning mostly. As you can see here, it uses the waist type anchor. If I write down picture, so the anchor will look like this, and it will be anchored in this hole. So these are the anchors, and this is the tendon, and when after cutting out the pre-stressing force, these ways will then lock in here and giving the anchor to the pre-stressing wire. Now the We also use high strength concrete for prestressed member, mainly because the members are subjected to high compressive stress. So we normally use high strength concrete for prestressed structures. We usually use more than 35 megapascal concrete in the prestressed concrete structures, but often concrete with 50 to 70 megapascal is used in these structures. And this is an example of prestressed concrete bridge in Japan, and they use it is in Tokyo, in Akihabara, the place called as Akihabara, and it uses the concrete of 120 megapascal. These strength, and these are called as ultra high strength concrete. These ultra high strength concrete were made using special lightweight aggregates, and these were used just to reduce the autogenous shrinkage in the concrete, and they were able to produce concrete with very high strength, almost 120 megapascal. Now, looking from the method of prestressing, it can be divided into two types. One is pretensioning, and the second one is post-tensioning, depending on if the concrete is cast before or after the prestressing of the tendons. Let's first look into the pretensioning. In the pretensioning, the member is pretensioned. The tendons are pretensioned before the casting of the concrete. So the steel is tensioned first, then the concrete is cast on the formwork. The typical advantage is that these are mostly done in the precast factory. That means there is a good quality control, and also once the pretensioned structures gain proper strength, they are transferred to the side, and it can be erected very fast. So the speed of erection for pretensioning is much faster than the other one. So this is how the pretensioning is done in the factory. They usually have this casting bed where the pretensioning wire is placed and the concrete is cast. So if you look into the steps, first what is done is the pretensioning wire. This is the tendon. It is first stressed, and on this tension tendon the concrete is cast. And after the concrete gained proper strength, the wires are cut, and the wire will then transfer the prestressing, the compressive force in the concrete through the bond between the concrete and the tendons. So after the wires are cut, it will transfer these compressive stresses in the concrete. And as you can see here, there is this camber due to this compressive stresses. Now, as you can see, the one limitation of this pretensioning method is that it requires very heavy casting bed, and it can be done mostly done in the factory. And also the tendon diameter are usually small. We use rather small diameters in the pretensioning because to improve the bond between the concrete and the steel, and and also it is easier to pretension as well. And normally we use multiple wire strand tendons for pretensioning. And also for the pretensioning of the members, it is difficult to change the profile of the tendon. So here this is the profile of the tendon that we wanted. So in pretensioning, it is usually difficult to achieve that one, but we can overcome this by two methods. First method, instead of changing the profile of the tendons, we can change the shape of the concrete itself. So the tendon remaining the straight line, we can change the concrete shape itself. That is one solution. And another solution is using these deflectors. We can arrange the tendons in the way we like it, but it is not very easy as the other method that we'll be talking soon. And we will talk about the profile of the prestressing tendon later on, why we want it in a different profile, not in the straight line. We'll talk about this one later on. So this is an example of pretension member. As you can see, these are the prestressed wires, And as you can see, there are no anchors in here because the force is transferred from the wire to the concrete through the bonding between the concrete and the steel. So in the pre-tension members, we do not need in anchors, permanent in anchors. And another method of prestressing is called as post-tensioning. As the name suggests itself, in the post-tensioning, the concrete is cast after the concrete is cast first, and then the steel is stressed. Now, as you can see here, the docks are placed inside the concrete member first, and the concrete is cast, and then the steel wire or the steel tendon is placed inside the dock and is tensioned. And after tensioning the steel, the end anchors are placed so as to lock the steel at the ends. So for the post-tensioning members, we need permanent anchors at the end to hold the prestressing wires and also to transfer the force onto the concrete from the wire. So again, the main difference between the pre-tensioning and the post-tensioning is that for the pre-tensioning, we tension the wire first and then cast the concrete on the tension wire and then cut the ends. And in the post-tensioning method, we first cast the concrete and we'll insert the steel inside the docks that are already being there, and then we tension the steel after the concrete gain its proper strength. And these docks that are used to put the pre-tensioning looks something like this one. They are usually thin corrugated metals through which we insert the pre-tensioning wire, pre-stress wires. And after the wire is being stressed, then these docks are filled with the cement grout. And as you can see here, the cement grout is being pumped into the duct. So this has two benefits. One, it will prevent the tendons from getting corroded, and second, it will help to improve the bond between the concrete and the steel as well. And we can also use PVC or plastic sheets instead of these corrugated metal tubes. So the one advantage of post-tensioning is that it is easier to change the profile of the tendons. As you can see here, for this beam with an overhang, cantilever overhang, the tendons are arranged in this shape. We'll talk about this tendon arrangement shape later on, but as you can see, but just remember that for the post-tensioning, it is easier to arrange the tendons in different shapes. And for this uniformly distributed single supported beam, the tendons can be arranged like this one. So it is much easier to change the profile in the post-tensioning. And there is a special kind of post-tensioning here. It is called as external post-tensioning. So difference is that the tendons or the prestressed wires are placed outside the concrete member itself. So as you can see here, these are the box girder, section of a box girder. And instead of placing these wires, these are the tendons. And instead of putting these tendons inside the concrete member itself, they are placed outside the concrete member. So you can easily see these tendons outside here. So these are called as external post-tensioning. And in this external post-tensioning, the load from the steel is transferred to the concrete through these deviator blocks or through this end anchorage. So I'll let you think about the advantage of external post-tensioning for a minute. So think about what might be the advantage of external post-tensioning compared to the internal post-tensioning, where the wires are inside the concrete element. So if you look in the figure, it might be more obvious. So you can see here it is inside the box girder, and you can see these are the ducts where pre-stressing wires are there inside. Now, as you might have already guessed, the main advantage is that it is much easier to place these ducts and the pre-stressing wires when it is external pre-stressing, because it is much easier to place, and also it will not occupy the space in the concrete members, so we can make concrete members much slender as well. And another big advantage is that we can easily inspect these prestressed ducts as well. So if there is improper gouting or if there is any corrosion in the reinforcement, we can easily replace these tendons, individual tendons. So it is much easier to replace individual tendons compared to the internal post-tensioning ones. So that is the main advantage of external post-tensioning. And here is a picture of post-tension segmental construction. These are the segmental brace sections which are transferred from the factory to the side and then are attached to the existing section using post-tensioning. As you can see here, these ducts and here as well, through these ducts the prestress post-tension wire are placed and then are stressed so that this segmental element is then attached to this existing member. So this type of method is much faster construction technique for the long span bridges especially. And the post-tensioning is also quite popularly used for precast building construction as well. For the precast building, the beams and columns are cast in the factory and then transported to the side. And at the side, the columns and the beams are joined together using the dry beam column joint using these post-tension members. So these are the post-tension member. So they are placed inside the beams and the columns and then are stressed to which will act as these dry joints. So this is another use of post-tensioning for the precast building structures. And again, these are the examples of the anchors that we use for the post-tensioning. So in the post-tensioning, we need to anchor the tendons after it has been stressed. And usually the waist anchor is quite commonly used for the post-tension members. And also we can use the butt anchor here, and as well as if it is a bar, we can use the thread system as well to anchor the bar after it has been stressed. And now these are some examples of the pre-stressed concrete members. So this is an example of the pre-stressed concrete pile. So these piles are used for high-rise buildings. As you can see here, these piles consist of these. There are a number of pre-stressed wires here, and they are locked using this end plate at the end. So these help as anchors at the end. And this is the installation of the pre-stressed concrete pile. In fact, this picture is from my PhD thesis, and my PhD thesis was about the lateral capacity of the pre-stressed concrete piles, and in fact this is me. So one of the use of pre-stressed concrete structures is for pre-stressed concrete piles as well. And another example of pre-stressed concrete members is segmental bridge piers as well. As you can see here, this pier consists of number of segments which are attached together by the pre-stress force. By the pre-stressing, these segments are attached together. And this is the modern concrete construction technique for the segmental bridge piers. But in fact, the ancient Greeks also utilized similar technique for construction of this pier. As you can see here, it has segments as well, and they are joined together by a heavy load at the top. So it will act as it will produce compressive stress which will hold these segments together, which is very much similar to the modern piers as well. And